And now we start our today's session. Once again, welcome back to this ground improvement technique class. This is week 5. I am Rajat Boni and I am from IITISM Dhanbad and I am one of the PMRF research scholar at IITISM Dhanbad and get a chance to teach or take a ground improvement discussion session under Professor Dilip Kumar Vaidya sir. He also taught this lesson in Nptel. So I am one of his TA in this ground improvement. So that's it. And our today's session will be planned like that. First, we discuss previous week's lectures in very quick session. In this, we discuss about the vibro compaction little bit. Then start our week 5 ground improvement lessons one after one, and then we try to solve few problems in this vibro compression, and at last we start deep replacement method for this week also, and after that, if time permits, we will discuss about any doubts regarding this session and try to solve previous year assignment problems and give some idea to solve the assignment in this course during this year. So now we start our session and I share my uh, presentation. Please wait. I'm sharing. I think the presentation is visible to everyone. Uh, Now we start. In previous week, I think visible to everyone. Start today's session. In previous week, we discussed about the rapid impact compaction and what are this application merits, demerits like that, how it is applied in the ground, and what are the different techniques is applied in this, how much blows use like 40 to 60 blows per minute, and also the diameter of the circular drop or temper or hammer is like 1 to 1.5, and there's also discuss about the drop of height like 1.2 meter and 5 weight is 5 to 12 meter. After that, we discuss about its suitability and its application, like it is increase the bearing capacity, stiffness, like that. And then we discuss advantages, uh, disadvantages, limitation. And then we try to solve few problems on that. And at the session last, we discuss about the please wait. We discuss about the uh, vibro compaction, a new topic. Just start, we introduce about the vibro compaction. In this we study, it is not completed yet. We today by today it is completed. Please wait, and I just go through it to understand, well understand before we started our session. So in this we discuss about the vibro compression. What are the basic concept, like it is used for saturated coastal soil like that, and one probe is there, and in screen it is attached to this probe, and the probe is inserted the ground and vibrated. Due to the vibration, frictional resistance between the particle is overcome and particle is close together. Like that, these techniques is apply in this field. So it is mainly there is one figure also we discussed that one probe is inserted and vibrated and there is some void space is created and fill this void space some in situ material and another again this compaction is done by vibration and like that we gradually upward to the ground surface and compact it. And we also discussed the suitability of this method. Like we discussed that this method is mostly suitable for positionless geomaterial up to 20% fine, but the clay percentage is between the 2 to 3% particle only. If it is more than the clay percent is more than 3%, this method is not suitable and very difficult to handle for vibration. And we also see that one graph about the fine contents and standard penetration. And actually, here standard penetration represent the strength of the ground. So it is see we see the so that previous week that the curve is going downward if the percentage of fine content is more than 10% or 3% like that. And if low percentage of content, then curve is going upward and more strength is given to the soil. And also discuss the what are the suitability for what zone it is suitable. Like it is mostly suitable for zone B, which is range for coarser medium, coarser sand to the coarser gravel. So it is mostly suitable. We also discuss with that and also discuss the about the application about it. What are the different why it is used, how it is used, and why it is used like that. That means it is used mostly for increase the bearing capacity like other method, and also most one advantage of this method is to increase the or mitigate the liquefaction on this method. It is very suitable to mitigate or important to mitigate the liquefaction because it is dangerable or vulnerable to the structure liquefaction. And also discuss the advantages and limitations. Like it is very quick, easy, economical, and disadvantage is that only one disadvantage is one or two. Like it is only used for questionless soil or with clay content less than 3%, and also it is induced some subsidence ground due to vibration. Is so few limitation, but there is more advantage than limitation. So also discuss the principle of vibro compression. Like we discussed that if you due to the vibration, particle to particle internal friction is removed or overcome, and particle much closer to there. And we also see that due to this vibration, due to the probe, which is created one acceleration. If acceleration is more than zero point 0.5 g, the this densification is valid. If it is less than zero point 0.5 g, there is no need to there is not possible to densify. So it is said that if acceleration induced by this probe is greater than zero point 0.5 g, then dynamic stress is induced by dynamic compression and destroys the structure of the granular and then particle is come to close to each other. And also see that if they further increase the acceleration, the shear strength of the soil will slightly significantly reduce. And also further we increase the up to 0.3 g, then further reduce and fluidize the soil. And we also see the four different zone related to this related to this compaction, fiber compaction, which is one is dilatory zone, which is very close to the probe. Another one is fluidized zone, and last two are compaction zone and elastic zone. And we saw that the most suitable compaction is happened at the boundary between the fluidized zone and compaction zone. So in last day also we saw that we described the one by one this zone and also saw that deep versus surface compaction. We saw that the deep compaction or vibro compaction is more suitable or more efficient than the surface compaction. It is because and one scientist, one scientist or researcher Arnold and Hartley to researcher is give the idea about by numerical analysis that when we increase the number of cycle, the depth of improvement or depth of area of improvement is increased from 1 to or radius of influence zone is increased from 1 to 4. And also we see there if void ratio is reduced significantly for deep compression than the surface compression. Then we discuss about the installation process, and we discuss the when we insert the higher frequency like 30 hertz frequency we apply to and up to the targeted depth, we vibration is reduces to 15 to 20 hertz to relate the soil natural frequency and resonance. Due to the applied resonance, we by low energy we increase the densification like that. We insert high frequency, then vibrated at low frequency, compression at low frequency, then extraction also you can high frequency by this graph. And also see one graph that if you increase the percentage of file, the compression degree of influence zone reduces. And if you increase the compression energy, degree of influence increases. So like that, we discuss all of these things previous. One today we start about some derivation. One is when we apply the vibro compaction, what are the how much ground subsidence is happen is derived from equation. And for this, we apply three conditions. One is when the subsidence happen, we without backfilling. That means we do not use backfill material or backfilling the material. And uh, and also we find the same thing is with backfilling. And its third one is we derive one that when during the backfilling, ground is subsidence too. So by that by derivation, three formula is derived. By these three formula is derived for ground subsidence. How much is ground subsidence and how much volume is required to backfilling and corresponding spacing also we required. And due to the subsidence also during settlement also, what are the volume change also we can find out. So like to find out this, I go through one another PPT. So where yes, it is like that. It is said that we take it from one ground improvement book. It is available every ground improvement books. No, don't worry about this. It is said the first one is volume change with backfill. It is from this three-phase diagram you can see that the initially the ground is like that void and solid. After that, when we apply the vibration, the ground is subsidized like some distance. You can say s. Sorry, some distance like s. So we can find out like this apply equation. We know that initially total volume of the ground V is equal to Vs into 1 plus E naught. Initially we find out that. After the ground subsidence, another volume is V1 is equal to the Vs into 1 plus E1. Volume void ratio is changed and total volume also soil is changed. By differentiate or by difference or subtract one V and V1, we get find out the volume of void or field is required. So like Vs is like by this equation. You can see that in the screen by this equation. And after that, if we divided the total equation by total volume like that, and we getting arrive this formula, that is S by H equal to E naught minus E1 plus 1 plus E naught divided by 1 plus E naught. So where S is the ground subsidence without backfill, you remember this equation is applied when we do not apply any backfill material. And H is the height of the or thickness of the field. And E naught is initial void ratio, E1 is after getting improvement void ratio, and like that we find out that. And second one is when we apply the backfill material. Due to applying the backfill material, up to that much is similar to the previous. Now we consider that the height of the diameter of the backfill is material is DCL. So we can find out the volume of the backfill by applying the pi by 4 DCL square into H. And if we put this in this equation, 3.29 equation, we get arrive something like that. This was equation. And here, if you replace the A, which is nothing but the influence area, uh, by the area by spacing, like for square space for square pattern it is s square, like spacing square, and for triangular pattern it is nothing but 0.865 s square, which is already discussed in this deep dynamic compaction also. And replace this, we can easily find out the spacing required for the backfilling or required for the compaction when we apply the backfilling. So we arrive two different formula. One is for triangular pattern and another is for square pattern. Only difference is in this is the coefficient. For square pattern it is 0.89 and for triangular pattern it is 0.95. Only remember these two things, and most of the formula is similar to each other. And third one, when we apply the backfilling material, sometimes ground is subsidized or settled down. And the settlement is we apply, say, we can say if S, you don't confuse about the S here. One is small s, another is capital S. And small s is represents the spacing, and capital one is represent the settlement when we apply the backfill material. So we modified our equation like that, and after doing same calculation, we arrive this type of equation. So by this way, we can derive different types of spacing for different patterns and different condition also. So moving to our previous slides, like which is discussed, like that we find out all the formula here. This one, this one, this one, and these ones. So moving to the next slide, here with one conclusion drawn there, that when the volume changes without and with backfill material presented in previous slide, we assume that the ground is soil is uniformly compacted. And in the field, it is not the same case, because when we apply, we assume that ground is uniformly complete. That means when we apply like square pattern here, 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 you can see my screen there. By square pattern, when we apply this ground improvement compaction point, so there is one influence zone is created for each point. Okay, so we assume that during our calculation, we assume that the uniformly the compacted this influence zone, influence area is uniformly compacted. But in the field, it is not the same, because the compaction is mostly happen around the or nearby the proof, and away from the proof the compaction is not inform is the same as this is in the near the proof. More compaction is near the proof and gradually reduce when the distance is increases. So when for that, when we apply the formula in the field or to measure the backfill material, some trial maybe go with. That means we one or two tests for vibro-compression is going, and by this test, whether the ground is subsidized or not, if it's subsidized, how much is subsidized, if you get more subsidized, then the backfill material is needed or not, like that. We calculate one or two compaction point, and this for one or two compaction point, this is applied to whole area. And another point is also drawn that this maximum material should be assist the compaction, because there is void space is created during this vibro compaction, and the probe is not compacted further because there is, due to this void space, the energy is not distributed equally surrounding the soil. So for that we apply some backfill materials, because due to the back compacted the field and energy is distributed and further densification is happened. And during this backfill replacement or material field, we actually, for more achieving compaction or more uh, desired value, we actually replace this backfill material with higher stiffness, strength, and permeable soil, so that we can improve our ground further also. So similar things happen like that. And moving to the next slide, we discuss about the different design consideration. First one is performance criteria. One scientist or researcher, you can say Alice, will based on the performance criteria, different performances, it is based differentiate based on relative compaction. What mean if you what type of soil, that means what type of construction you need and how much relative density you need. Based on that relative density, we need to improve our ground. So like that, if we improve like for slab, flat bottom tank and embankment, the relative density should be more than 60%. And if we increase for we use this method for column and bridge foundation, the relative density should be in between 70 to 75%. And for machinery and mat foundation, the relative density should be greater than 80%. Because we set our goal like that, because for column footing and the bridge foundation, it is very critical, because if the strength is not suitable for column, one or two column may settle down. Due to this settlement, differential settlement, there is crack happen in this structure, and the structure may be collapse. So it is more important for column that the relative density should be more than for slab, which is applied. And we also designed our relative density like that. For less relative density, applied energy should be less, and for higher relative density, more applied energy to be applied to the ground. So if that means if we apply the relative density 80%, more vibration is created and more energy applied to the ground. And this type of improvement is happen when the importance of the project is high. That means if we apply for machinery foundation or for mat foundation, uh, which is constructed by this foundation, which many heavy construction is or building is situated by this construction foundation. So for that, higher compaction should be needed. Moving to the next slide, another design consideration is the area and depth improvement. We know that already discussed in previous ground improvement technique is that the area depth of improvement, or the area of influence should be greater than or larger than the compaction point or footprints of the foundation. So in the next slide, you can see that here we draw some figures that this the box, rectangular box or square box, is nothing but the footing. In this footing, we can see that one or two points are compaction point is happening. So you see that the compaction should be like that. The influence area should be greater than the footing, footprint of the footing or area of the footing. So if the footing area more is big, the more number of compression point is needed. Like is here, we and we also for critical point we also apply the compaction point like that. And if it's steep footing, we use like that. So it is discussed that it is essential that the area of improvement is larger than the footprint of the foundation. And it is also discussed that one or two rows of compaction point may be installed outside the footing. It is not that every time we inserted or compacted our zone in between the footing area, not like around the footing also or outside the footing area also, one or two rows or columns maybe compaction point may be installed because the load is not the which load is coming from the column, it is transferred to the footing. And footing is not like that, is directly transferred to the ground in very deep. It is distributed the load to the surrounding soil. That means the loading area, distribution area is greater than the footing area. That's why the surrounding soil of the footing area also be improved, need to be improved. And if the liquefaction possibilities happen, 2 to 4 rows may be compacted by this way also. And here it is one another point is discussed that the depth of improvement should be deeper than the depth of problematic geometry to eliminate the potential problem. We also know that for safety purpose, that means if the our ground is like that and we need to improve our ground from here to here, that means up to that much is problematic soil is present. We need to improve our ground through the vibro compaction. If we need to improve our ground for safety purpose, we actually need or should be improve our ground slightly greater than from the depth of improve, slightly greater than our problematic soil to reduce the risk. So that so this is done in this field. Moving to the next slide, we discuss about the grid pattern and pacing. We know that in previous also we discussed about the to deep dynamic compaction that there is some pattern is needed to improve the ground or apply the energy. So here also some pattern also apply like square pattern, rectangular pattern and triangular pattern based on the ground suitability, ground plan area, availability, accessibility and also the type of material like that. But the spacing between this point, compaction point, should be in between the 1.5 to the 3.5 meter. And it is depend mostly on the type of geometrical, density of geometrical, and target density of the geometrical after the compaction. And also depend on the horsepower of the vibrator. So for by this one or two ground one or engineers are given the charts where we can find out the spacing based on some points like tributary area and the degree of compaction or the relative compaction what is tributary area? Tributary area is nothing but the influence area. If like the if we apply square pattern, if we apply the compaction point in square pattern like here, 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 for each of the compaction point there is some influence area. That means the each of the compaction point is governed or compacted up to that much area. Based on this area or influence area, we can find out the spacing of our patterns, different patterns like square pattern, triangular pattern, and rectangular pattern. So this influence area here it is nothing but tributary area. So here we can see that one graph based on the different types of geometry. Zone A, Zone B, Zone C. Zone A is represent the silty soil with 5 to 15% silt. Zone B is represent the uniform fine to medium sand, clean sand, and Zone C is represent the well-graded clean sand. So we can see that it is the graph is based on relative density upon the surface area or tributary area. We can see if we targeted, if we say that our targeted compaction point is the relative compaction 75%, and our soil is like zone A, relative zone A, silty sand, and silty sand like that, our soil improvement. So by this chart, like 75%, you can draw like this line and vertically draw from this point like that, like that. Our tributary area should be in between 2.5 to 4.5 meter based on our suitability or our cost of improvement. That means for zone A, 75, and for relative density 75%, our tributary area should be in between 2.5 to 4.5 meter square. And by this tributary area, we can find out our spacing also. So here one another aspects also given to find out the spacing there. During the subsidence, average subsidence happen during the vibrocompaction, and if the subsidence is more than our required subsidence or ground settlement, then the backfill is needed. During this backfill material, another spacing formula also we can derive in previously. By that formula, we can also find out the spacing also, like here and here. You can see that. One is for square pattern, first one is for square pattern, and second one is for triangular pattern. So by this formula also we can find out our spacing based on our backfill material, whether it is backfill needed or not. If backfill needed, how much backfill material needed? Based on this backfill material or influence area, we can find out the influence area, and we can also find out our spacing. And also we can find out spacing based on the bearing capacity formula. So one or two charts, one two charts is given also based on the bearing capacity formula. You can see that the allowable bearing pressure limited to the settlement up to 25 mm versus spacing during the vibration is one chart is given. If our targeted achieve targeted bearing capacity is 500, or we can say that is 300, the spacing should be between the one to between two compaction point should be 2 meter based on the bearing capacity formula. So we see that by three formula or by three ways we can find out spacing. One is based on the materials type and relative density, geometrical types and relative density. One chart is given. Based on this chart, we can find out the tributary area, and based on the tributary area, we can also find out our spacing. And another way is based on the backfill, whether it is backfill or not. If it is backfill, some spacing formula is derived. We can also see in this session, previous starting session that during square pattern and triangular pattern, some influence areas created, and based on that, our spacing is derived. And another one is based on the bearing capacity formula. Bearing capacity, that means if the chart is available for bearing capacity and we need to improve our soil based on the bearing capacity, then this chart is applied. So like that we improve our ground. So moving to the next lecture 4 in module 5, that is let's discuss about the different types of design parameter and procedure. So the design pattern for fiber compression is nothing which is governing the, or mainly we can say the factor which is depends on the govern the design of the vibro compaction. It is nothing but we already discussed the geometrical type, fine content, percentage of clay particles like that. That means geometrical type, whether it is questionless soil or cohesive soil, we know that it is suitable for questionless soil only. And whether fine constituents is present or not, if fine constituents is present, how much fine constituents is present, like it is suitable for 20%, and percentage clay in between 2 to 3% it is suitable. And also we know that this technique is improve the ground up to 40 meter, mostly for relatively for 20 meter, but it can go to up to 40 meter. So it is also depend on the thickness and depth of the porosity geometry, and it is also depend on the depth of groundwater table. Like we know that the influence, if there is groundwater table is present or whether it is not, the biocomposition is suitable for both the case. And also it is depend on the initial void ratio and targeted void ratio. Based on the initial void ratio and targeted void ratio, we can find out the relative construction for each of the case, and to achieve our target, to find out the targeted void ratio, and by that way we improve our ground. And it is also influenced by the spacing and pattern also, like whether it is a square pattern, whether it is triangular pattern or not. And we also see that the depth of improvement, area of improvement should be larger than the footing area, always larger than the footing area, because the load of the footing should always distributed in triangular pattern or like more than the uh, footing area. So we need to address the ground more than or area more than the or we also need to the address the ground surrounding the compaction point also, or surrounding the footing also. Moving to another others design parameters like equipment type, horsepower. We see that more the horsepower or more the energy is created, more vibration is created. So if more vibration is created, ground is settled, is relative compaction of the ground is more, like 80 to 90%. So based on this criteria also we can select our equipment, whether if we go for footing or column footing or for slab footing, the energy is required less. If we go for the mat foundation or machine foundation, energy requirement is higher. And also it is depend on the frequency of penetration, compaction, extraction. We see that when we penetrate or inserted the ground, more frequency is needed. And after a certain targeted point, the NF frequency should be matched with the really ground frequency, that way soil frequency, to apply the resonance. Due to the resonance, more compaction is happening, and after that, during extraction also, the frequency is more than the surrounding soil. And like that, extraction, penetration, and compression and happening. And also it is dependent on the duration of the compaction. That means if we apply the energy, how much time we apply this energy. If more application is, that means 30%, 30 second, more than 30 second, or 1 minute, more compression or more vibration is generated. If sometimes it is suitable, sometimes it is not suitable. Due to the more vibration, ground should be soil should be like fluidized, so fluidized in nature, and whether you improve the ground, it is not. It is destroy the soil structure, and it is actually uh, can actually uh, we can say that um, fluidize the ground, so it is not suitable in this our case, like that. And it is also we can see the ground subsidence also. If it is more subsidence, more backfill material is needed, and we also need to find out the diameter of column. Moving to the next slide, we discuss about the procedure, how to apply this biocomposition in the ground. First of all, we need to find out the geotechnical profile and potential problem, and also determine whether the groundwater table or not, and whether it is suitable for biocompression or not. That means if it is questionless soil, if it is questionless soil and percentage of fine is less than 3%, 10%, and clay content is less than 3%, this method is mostly suitable. So like that, we can find out whether it is suitable or not. After suitability, we can find out the relative density of the initial relative void ratio and relative density of the void, and we need to find out our performance requirement. That means for what purpose we need this vibro compression, whether it will address increase the bearing capacity, whether we need to address the settlement criteria, or whether we mitigate the liquefaction. After selecting the performance, so like bearing capacity, settlement, and liquefaction, we need to find out the targeted void ratio based on this criteria, bearing capacity for uh, each of the performance criteria, and we need to find out the relative density. After that, we need to find out the spacing based on this relative densification. For find out the spacing, we apply some formula like volume change without backfill, volume change with backfill, again volume change with backfill, and also the ground settlement. Based on this, we can find out the ground subsidence also, spacing also, and we also need to address that whether the ground subsidence is greater than the requirement or not. If it is greater than, backfill material should be used to minimize the ground subsidence. Moving to the next slide, we discuss about the construction. It is nothing but we describe the equipment which is needed for vibro compaction. So we need like we also discussed that for shallow compaction we need the smooth wheel roller, seafoot roller equipment. For deep dynamic compression we need the temper, hammer, crane, like that. For rapid impact compaction, rapid impact compaction, we need the one excavator and hammering. Like same way for vibro construction also we need some equipment. One is crane, another one is hydraulic and electric vibrator, another one is probe, and last one is water pump and air compressor. And also we need some good backfilling material to improve or compact the ground very well. So here we discuss one table for different vibrator. No need to go with this in detail. For this, we just look into it and go to the next slide. In the next slide, we will discuss that the vibrator commonly used to penetrate the probe into cohesionless geomaterial and densify the geomaterial by vibration. That means we also discussed this point previously that it is only suitable for cohesionless geomaterial. And water is sometimes introduced to help the liquefy the geomaterial during the penetration and densification. That means if we apply the water actually remove the resistance. Or we can it is apply or use like liquid lubricant type. So it easily overcome the uh, particle to particle inter friction, and also when we apply the water, liquefaction potential should be happening. Due to this liquefaction, particle to particle force is reduces, and particle is very calm, very close to each other. Like that, we apply vibroconvection. Moving to that, when we apply this vibroconvection method, the position of the probe should be accurate and desired location also. And also turn on the water and power and check the pressure and voltage to ensure the equipment function very well. And in second point, it is discussed that sink the probe into the ground at a rate of 0.3 to zero point 0.5 meter per minute and observe the variation of electric current. to reduce the rate of penetration if the current is too high, and reduce the water pressure when the probe is close to the desired depth to minimize the disturbance, and also the continue the probe to the desired depth and maintain the vibration for at least 30 seconds. So in this section discuss that we while find out or point out our compaction point before or apply the vibro compaction by some preliminary calculation. After that, and some trial also. After that, we apply the water force and vibration force. We insert the probe into the ground at a rate of zero point 0.3 to zero point 0.5 meter per minute. During this high energy, apply the ground, and after reach the certain targeted point, we stop the water pressure or reduce the water pressure and give some time like 30 seconds to 40 seconds and to maintain the vibration and that targeted point and need to improve the ground. Okay, so moving to the next slide. The same when extraction also same rate is applied, same zero point 0.3 to zero point 0.5 meter per minute, and after that also extraction same again penetrate re-penetration happening, again extraction re-extraction is happening. Like that way ground is compacted. That means if you draw one figure, one column is draw first, due to this force, water force and vibration force, prove is like that one targeted point is reached. After that targeted point, give some time to vibrate here and improve this ground. And after that, we extract the scope and depth level. And again, some times is given to vibrate this area and then and improve like that. And gradually, we go upward in this process up to the ground surface. And during this compaction, we apply the backfill material also to occupy the void during the this compaction. Like that, this test is apply in the field. So moving to the next slide, that is lecture 5 in module 5, you can see that uh, for different for different pattern like square pattern and for triangular pattern different, we also discussed that different influence zones happen. How much that influence zone is equivalent, we can find out now. So it is said the equivalent radius is that nothing but the effect of each compaction point is extended to the end of its equivalent radius, which differ for square and rectangular arrangement. That means when the square pattern is happening like that, like that, here it is point compaction point, here one compaction point, here compaction point. So for each compaction point, one equivalent influence area is created, and this equivalent influence area is represented by one radius. It is nothing but the equivalent radius. This equivalent is radius is find out based by the spacing, which spacing of the spacing in between the two compaction points. So we can see that for square uh, enclosed grid, equivalence area is square of the spacing, that is s square. If we replace this s square to the one equivalent circle, that is pi r square, we can easily find out the equivalent radius r, which is nothing but the 0.5. Please wait, my network is lost. Please wait few minutes. 15. I think we're coming back. My network is uh, disturbing. So sorry for that. I think it is now okay. So the discussing that for square pattern, this influence area is nothing but the square of the spacing. And if we replace this square influence area by one equivalent area, square area by equivalent area, hello, equivalent area. So, uh, and by this formula, we can find out that R is equal to 0.564 S. S is nothing but the spacing of two compaction point. So, like that, we find out the influence area. For square triangular pattern also, we can see that we find out the influence area also. It is nothing but the influence area is nothing but the 0.865 into square of the spacing. So we see that the triangular pattern is created influence area one hexagonal is created by this triangular pattern. So by calculation, by based on the finding of this defined calculation, we find out this area is nothing but the hexagon area. It is nothing but the 0.865 s square. By this, if we replace this area by equivalent circle, that is pi r square, we can easily find out the equivalent radius. That is nothing but 0.525 s. So it is said that a hexagon is formed by bisecting for various grid lines joining the adjacent grid. Like that way, we can find out for its equivalent area for different pattern. For square pattern, it is simply s square. It is means spacing square, and for triangular pattern, it is 0.865 s square. It is very important with regarding to your assignment problem, also to your exam purpose also. Now we try to solve two problems regarding this vibro compaction. So first one is it is said that in first problem it is said that a 8-meter thick loose and sand exists in a site that has a fine content of around 10% with nominal clay particle. The minimum maximum void ratio of the sand are given 0.425 and 0.825 respectively. This sand has an initial void ratio 0.6 and the design required of the sand is to densify the targeted relativity 75%. Estimate the required spacing of compaction point in a triangular and square pattern and average ground subsidence after the vibro compaction without backfill material. Remember here it is said that without backfill material. This is very simple problem. To solve this problem, we need help one chart. We also previously discussed this chart to find out the spacing for triangular pattern for and rectangular pattern. So it is given that our targeted relative density is 75%. So by this chart, and our soil is in between 10%, uh, uh, content fine content is 10%. So it is belong to zone A. Zone A is said that centizen is in between 5 to 15% C, and in our case it is 10% C. So we use zone A in this car, and our targeted relative density is 75%. So targeted density is 75%. So you see that by this chart, 75, from this 75, if you draw a horizontal line which is intersecting zone 1 at this point, and zone 2 is at this point, and if you draw one vertical line from the two intersection point, we can arrive at one tributary area in between 2.5 meter square to 5 meter square. So we assume that our tributary area is 4 meter by this problem. Now, after that, now we go through another slide of solution part of this problem. I solve this in by hand. That from this graph, we assume that our tributary area is 4 meter square. And in this question, it is asked that have to find out the spacing for triangular pattern and also for square pattern. So we see that for influence area for square pattern, it is nothing but the spacing square, and we replace this influence area, that is also called as territory area, by 4 meter square. We easily find out that the spacing for triangular pattern is 2 meter. For square pattern is 2 meter. For triangular pattern, the formula is little bit modified, that influence tributary area is equal to 0.865 s square. So by this formula, the spacing is like that, 2.15 meter. So we easily find out by these two formula for square pattern and triangular pattern, spacing is easily find out, which is also help to you. This problem is also help to your assignment also. And after, and second question is given there in this problem, you also find out the subsidence after the vibro without backfill. For that, we need apply this formula, that is S by H is equal to E naught minus E1 divided by all divided by 1 plus E naught, where S is ground subsidence, H is thickness of the layer, and E naught is initial void ratio, E1 is final ratio. Here in this question it is given only E naught, H not given, E1 is not given. So we have to find out that. So for that we applied the relative compression formula. In relative compression, we can see that relative compression is equal to E max minus E1, that is we have after the void ratio after the compaction, divided by E max minus E minimum, that is maximum void ratio and minimum void ratio. So if we our targeted in question, it is given that our targeted relative density is 75%. So if we put this all this value in this equation, we also find out our void ratio after the compaction, that is 0.53, and all the values which you get from this equation, if you put this equation, that is h s by h is equal to e naught minus e1 divided by 1 plus e naught, and we find out the ground subsidence without the backfill material. So it is coming out that S is equal to 0.35 meter without backfill material. So easily we can find out by this formula. And these questions is also important for your assignment problem also. Similar type of question is framed in your assignment problem. It is helpful to solve the assignment problem also. Now we can discuss second problem, which is discussing week 5, that is a site consists of uniform medium sand with 5 to 10% fine content. The thickness of the sand layer is 10 meters starting from the ground surface. The initial relative density of the soil was 30% and analysis shows it is highly liquefiable. The minimum and maximum void ratio is given. It is nothing but zero point 0.5 and 1.02 respectively. The groundwater table is at 1.5 meter from the ground surface. The vibro compaction backfill with granular material is proposed to densify this possible liquefied soil with a targeted relative density is 60%, and to prevent the liquefaction, assume the average diameter of the granular columns can reach 0.75 meter and length of the granular column is uh, 10 meter and the ground subsidized by 50 mm. After the installation, determine the required spacing of the granular columns of a square pattern to eliminate the liquefaction potential. You can see that the problem is very big in reading, but it is not like that. It is very simple problem, and similar type of question is also is given in your assignment also. It is if all the values are given here, we, we can also you need to find only the spacing for square pattern only. If you remember in the starting session, we discussed about that volume change for backfill material with backfill material and also with settlement also. If we quickly go to the first slide in this session, you can see that two formula is discussed here. One is for square pattern, another one is triangular pattern. While the backfill material is backfilling and also ground is settled down also. So here we can use first one, that is S is equal to 0.89 dc root over 1 plus E naught H divided by E naught minus E1 into H minus 1 plus E naught into S. Here all the values are given in the question. We only need to put all the values here and find out the result. So going to the our problem, it is that maximum void ratio is given, minimum void ratio is given based on the maximum and minimum void ratio, and targeted relative compression also given. By these two or three, we can easily find out the E1. After finding the E1, then we apply the formula where everything is given. H is given 10 meter, H is given 10 meter, then diameter of the backfill material or column is given zero point 0.7 meter, round settlement is given 50 mm. All the if we put all the value, you see that sorry solved here. If you put all the values, the spacing is coming out is 2.4 meter. If you see that E naught is given, H is given, S here capital S is settlement, small s is spacing, and DC is given is 0.75 meter, and we have to find out only E1 based on our relative density formula, that is dr is equal to E naught E max minus E naught divided by E max minus E minimum, like that. We find out the E1 only, and all the value if we put this equation, we easily find out our spacing for square pattern. Remember here it is said that square pattern to find out this formula for square pattern. So like that we uh, uh, solve different types of problem for vibro compaction. So moving to the next slide, we discuss about the quality control and quality assurance. In quality control, actually quality control is need to address during the test or during the installation of vibro compaction, and quality assurance is test after the compaction whether it is achieved our goal or not. So for quality control we need to check or need to handle the sorry, we need to check the location of the compaction point, also need to check the depth of penetration, up to how much targeted depth we need to compact it, also need to check the vibratory power consumption electric current also. That means up for if we go to the footing we need low energy, if you go for mat foundation need high energy, for high energy high vibration is needed, for low energy low vibration needed, and also for during penetration compaction extraction frequency also maintained. That means for penetration and extraction high frequency is needed, already we discussed all of this thing, and for compaction the frequency should be in between the soil frequency, so that resonance should be happen. And we also address the we need to see the depth of obstruction, whether anything obstruct our probe or not. If it obstruct, we have to remove that obstructed material, and also need to look after the ground substrate. If more ground is subsided, ground is backfilled by the good material, strong material. If it is not, so don't. There is no risk here. Moving to the next slide. The same thing is written that we also check the water pressure, whether water is up, maintain the water pressure or not. Also, we have to check the good ground backfill material to improve the ground, and also go to some trial test for finding out the required spacing or not. Uh, Required spacing like that. Now come to the quality assurance. So, like other tests, like deep dynamic compaction and shallow compaction, we here we also go with the quality assurance by some specify well-known tests like SPT, CPT, plate load test to find out the soil strength after the compaction, whether it is achieved our goal or not, whether it is suitable for further construction or not, like that. So this test should be conducted. This trial test should be conducted at the center of the pattern of the compaction point. That means if we go with the square pattern like that, like that, this SPT-CPT test should be is a square pattern. This SPT-CPT test should be conducted center of the pattern. That means like the center here, this HTTP test should be conducted, and we find out whether it is after the SPT test we find out whether this ground is suitable, the compression is achieved our goal or not. So by this whole vibration process is completed. Now we can discuss the deep replacement technique, which is quite similar to the vibro compaction method. So for starting the deep dynamic compaction, I think we need some break, few minutes break, 5 minutes. I think this is okay. So after the break, we start a new topic in this module also, module 5, that is deep replacement technique. So I think now we take some 2 3 minute or 5 minute break. After that, we again start our session. So please stay on the line. Don't leave the session. I discuss the deep replacement method, which is very important for your exam purpose and also for your assignment purpose also. Few question is framed based on this deep replacement method. So don't leave the session. I will be joined after 5 minutes at 9:20. It is very simple and very quick in two lectures. It is described very small section. So don't leave. I after 5 minutes I will join. So welcome back again in this session. Now we discuss. I think I am visible and audible also. Now we will start the deep replacement method. So it is said that the deep replacement method improves the ground to a great depth and partially remove or displace problematic soil. And this problematic replaced by a better quality and density fill or a concrete in a column to form a column. This column and surrounding geometry form a composite ground for foundation to carry the vertical loads and shear force. So it is nothing but quite similar to the vibro-compaction method. Here we can actually, in what happen in vibro-compaction, we actually not replace the soil or displace the soil. Actually, we vibrate the soil and compact the surrounding soil. And if there is any void is created, this void space is filled by the same material, in situ material, and compacted again. So, but in deep replacement method, which is also similar type to the hydrocompaction method, eh, and also it is applied for a great depth like 40 to 20 to 40 meter, like hydrocompaction method. Here and but here we replace or displace the problematic soil, replace by different equipments, and this replaced volume is filled by the some good better stiff strength material and form a column type soil column compaction column like that. And this soil column and the surrounding geometry form a composite material. Composite material in the sense the soil plus some good another material which is not belongs to that institute material and form a vertical structure, vertical column, and which is carry the vertical load also and shear force also. If you see in the next slide, there is describe different types of deep replacement method for different techniques, like whether it is partially removed or whether it is partially displaced or not. The first one is it you can see there first one is called is vibro replacement technique. The vibro replacement in this technique actually we applied the some water jet. By this water jet we create a slurry. After removing this slurry we inserted some good material, stiff and dense material, and like that we vibrating this good material, and after that gradually increasing and reach to the ground surface and one compacted uh, material zone is created. And second one is vibro displacement. Here we apply some air jetting and replace or displace the surrounding soil by air jetting, and we fill this column with a good material through a feed tube. Like that it is created. And third one is vibro concrete column. Same one tube is inserted in the ground and concrete is inserted in the place on the ground through this tube and feeding tube, and like that one concrete column is created and improve the ground. Fourth one is control modulus column. It is actually one tube is inserted, and by this tube some good grouting material is injected to the surrounding soil. After that, the probe is lifted, and again the grouting material is inserted, and like that, once vertical column is created, which is good and most well known for other techniques. This one. And fifth one is sand compaction column. Here one casing is inserted in the ground and this casing is filled with the sand. And this casing is filled with sand, and like that one vibration, after vibration one uh, sand column is created. And another one is sixth one is encased granular column. Here we can same sand column like one casing is inserted in the ground, and after that one synthetic encasement also inserted, and in between that some good stiff material like stone and other boulder type material is inserted, and like one stone column type is column is created. Seventh one is ramped aggregate column. Here we can use reverse uh, flight agar. By this agar, we replace or remove this problematic soil. After removing this problematic soil, we apply allow some good materials, and after that, we by hammering or reamering, we improve, and one column type or composite material type was created. And last one is dynamic replacement. Dynamic replacement is quite similar to the deep dynamic compaction. Here we can use same one temper is used and one crane is used. After heavy weight is falling by this crane, temper heavy temper is falling by this crane, and some subsidence or crater ground crater is created. After that, we fill some good material, fill the crater some by the some good material, and like that continuous process is created, tempering or creating, and one column is created. So we now discuss one by one different types of uh, this technique. Here we say already discussed that the one is partial remover technique, another one is displacement technique. In partial remover technique, it is come under injecting water into the ground and turning the geometry into slurry and flushing it, and one hole is created in figure A. That means first one. It is come under partial removal. And also G, that means this figure, it is also come under the partial removal. That means a drilling hole is created by some reverse flight over, and after that good geometry is in place, or and then one column is created. Then second one is displacement method. It is created by injecting the air into the ground, or also by creating by driving a steel casing into the ground. And also it is also created by a reverse flight displacement auger, and also by dropping a hammer or temper to penetrate into the ground. By this four method, we use displacement of the soil in the ground. So, moving to the next slide, we discuss about the partial removal and partial removal and displacement technique, which is suitable for what type of soil. Actually, during partial removal, it is not affect the surrounding soil, or little effect during the surrounding soil. But in case of displacement method, the surrounding soil material is affected significantly, and also it is depend on the soil type, and the this displacement method is suitable for cohesionless and unsaturated soil, and but it is not suitable for saturated clay soil or saturated cohesive soil. For that case, we use the partially removal method, because if we apply the displacement method in cohesive saturated soil, heaving and lateral movement is created. For that, the proper densification is applied to the ground. And also, for displacement method is not suitable for sensitive soil, because in sensitive soil there may be some reduction in strength may happen. For that, uh, for that, this method is not suitable for this sensitive soil. Moving to the next slide, here we can discuss about the vibroconso versus deep displacement. Which method? What is the difference between this technique, which is quite similar to each other? Here we said the vibrocompassion method, which densifies in situ soil by driving a vibrating pole into the ground, is considered a deep compaction method and has been discussed under vibrocompaction. Most vibrocompaction methods involve use of backfill material like a deep replacement method. So it is quite similar to the deep replacement method, But the key difference is that vibro compression densifies geometrical in situ, while deep compression replacement method form a composite foundation forming a column of replaced material together with the surrounding soil. So the key difference is that during the vibro-compression, if the void is created, the void or subsidence is ground subsidence is filled by the in situ material only. That means the test is whether where the test is created or conducted, the same material is in replay or placed backfill in this uh, subsidence or in this void. Same material is filled in vibro compaction. But in case of deep replacement method, we use different type of material, different type of good material, stiff material. With strength point of view, it is very hard and form a composite column-like structure. Composite in the same means the different to different type of material used. One is surrounding soil, which is already is there, and another one is which is incorporated or which is filled or backfilled by good material. By this two material, one composite, one like type section or column is created, which is called composite column. Here also said that replacement of soil and densification column involves the densification of the surrounding soil and is similar to the vibro compaction. Partial remove is more suitable for the cohesive soil and replacement method is suitable for both cohesionless soil like that. Moving to the next slide, we now discuss one by one different types of deep replacement method. So first of for technical purpose, first one is vibro casing method, second one is vibro probe method, third one is reverse flight replacement method, and fourth one is dynamic replacement method. Now one by one discuss this technique and what are the suitability, what type of soil it is suitable, and what are the advantages, disadvantages, and also we discuss the how much depth we depth of improvement we can up to how much depth this technique is used. So first one is vibro casing. So in vibro casing, it actually driven or control by vibration, we driven one steel casing. The steel casing is enclosed at the bottom, and we driving the steel casing into the ground through vibration only. After that I backfilling this into the through by granular material through the casing. After that, we densify the fill material by repeated extraction and penetration process. That means first we inserted the steel casing through a vibration which is enclosed in at the bottom after we fill the backfill material into the casing and again we apply the vibration and repeated vibration and for extraction and penetration like that the ground is compacted. So moving to the next slide, here we discuss about the vibroprobe method. Vibroprobe method also called the dry method. Here we apply the pressurized air to replace the surrounding soil. After that, we apply same granular good material like granular fill and vibration is applied by vibration probe and like that ground is compacted. And third one is reverse flight displacement method. In this method, we apply one agar, reverse flight agar we apply. By this uh, reverse flight agar, we displace the soil, and this displace one column is void is created. This void is filled by some good grouting material, which can design at the laboratory or some other means. We can control the strength of this material, grouting material, and we fill this grouting material to this void space. And one uh, good strength and modulus column is created, which is related to our project. That means for our project purpose. This method is quite popular and also expensive. because in this method we improve the ground based on our requirement. That means we need to improve or strengthen our ground like 200 kPa. For that, we control. For that, we need some grouting material which is designed in the laboratory. Like that, we improve based on our requirement. We improve the ground. The last one is a dynamic displacement. In dynamic displacement, we actually using same deep dynamic compaction. We actually one crane and one tempering is using heavyweight temper is using. This temper is following quite a high, uh, quite a large height, like 40 to 30 meter, and we release it, freely drop it, and ground is subsidized and categories form. This category is filled by some good backfill material. Again, this temper is used to compact the ground. Like that, one after the ground is compacted. So that means first we compacted that much of ground by tempering, fill the material. Again, then we can compacted that much of uh, ground, fill the material. Like that, we gradually go upward and ground get one composite column is created. So now we discuss about the suitability. The suitability about the uh, vibro replacement method and vibro compression method. We can see that one graph is one chart is here given by based on the percentage final and ship size. So we see that the vibro compression method is mostly suitable for gravel to fine or coarse sand. It is mostly suitable, but for finer sand or fine material to clay material, vibro replacement method is most suitable. So based on the geometrical type, that is particle size also, we need to apply different types of technique. We also select the different types of technique. That means for granular soil, like we can say the cohesionless soil, most suitable technique is vibro compaction method, which is quite similar to the vibro replacement method also. But the vibro replacement method is suitable for the fine grain cohesive soil like silt, also some fine sand also. So here it is said that for vibro replacement method, this technology is mostly suitable for cohesive soil with undrained shear strength higher than 15 kPa. That means undrained shear strength means UCS. Undrained shear strength means UCS. It means it is if we greater than 15 kPa, then this vibro replacement method is mostly suitable. And it is this technology used for cohesionless soil also. And this for if we apply this technology for cohesionless soil, this is termed as vibro compression method, which is also we elaborately discussed in our previous lectures. And this method is suitable up to 10 to improve the ground up to 10 to 15 meter. In next slide, we discuss about the vibro replacement method. We know that two types of technique is one is replacement method, another one is displacement method. So replacement method is suitable when the shear strength is greater than 15 kPa and it is suitable up to 10 to 15 meter. And vibro displacement method, which is nothing but apply for suitable for insensitive cohesive soil with undrained shear strength from 15 to 60 kPa, and for that one stone column is created. That means we apply some technique, air jet or some steel casing, we displace the surrounding soil. After that, we will backfilling with good geomaterial like stone or granular material like sand, and we created some column type structure. This column structure which take loads from the surrounding soil and improve the ground. And some for most commonly used for vibro displacement method is stone column. But the sometimes also we can use the vibro concrete column. It is suitable for very soft clay. This vibro concrete column is suitable for very soft clay and organic soil because it is not able to provide sufficient lateral confinements to the stone. If we apply the stone for very soft coir, during the compaction, the stone may be displaced or the surrounding and the confinement pressure is not created and ground is not suitably compacted. For that, we apply the concrete because uh, uh, after the construction, concrete construction, or after the curing period of the concrete become hard, and it is um, uh, it is very good to take the surrounding load or stress by itself only. No need to distribute the load in surrounding. It takes the loads by itself only. For that, the vibro concrete column is suitable. And this technique is also suitable for 15 meter, 10 to 15 meter depth. The third one is reverse flight displacement method. We already discussed this one reverse flight auger is used. By this auger, remove or displace the surrounding soil. After that, some design or improved grout material is inserted in this void space and grout is improvement. So by this technique, we created a one contour modular stiffness column, and this method also known as control modular column. And this method is mostly suitable for loose sand, uncontrolled field, soft clay, and sealed organic soil, including peat, because this type of geometry have very less bearing capacity. They are able not able to support uh, some load also and very dynamic in nature also. Volume change is quite high. So for that we apply some control modulus column which is applied by reverse flight method, auger method. And this technique is mostly suitable for up to depth for 10 to 20 meter and most popular also and quite expensive and most popular also because it gives best result for all other deep replacement method. Because we control the strength in laboratory and apply to the ground. Then it is we discuss about the now discuss about the sand compaction column and stone column like that. In sand compaction column, it is suitable for the cohesionless and cohesive soil also, but the function is different for different. If we apply the cohesionless soil, it is coming under the vibro compaction method. If we apply the cohesive soil, it is coming under the vibro replacement method. And this technique is very suitable for higher depth. That means up to 70 meter. If we have to improve the ground up to 70 meter or 50 meter, this technique is very suitable. The next one is dynamic replacement method. In dynamic replacement method, it is suitable to improve the cohesive soil and soft organic soil. Because in dynamic replacement, we apply the temper. Due to the temper, one category drop a temper, high heavyweight temper. Due to this temper, one category is formed. After form catar, one backfilling the catar by good material, uh, and after that again temper is applied, and like that ground is compacted and surrounding soil is stabilized. So this method is suitable up to a depth of 8 meter. But the diameter of the column is rather larger because we apply depending on the temper. Because we drop a temper, the temper is sink and created the same size one void in surrounding soil. So like that we apply in this graph. So moving to the last slide in our last session, so lecture, in lecture 7 in module 5, we discuss about the advantage and disadvantage of the different types of a deep replacement method, which is already discussed. First one is sand column, sand compaction column. Advantages are it is low cost material because less expensive because it is readily available in the surrounding field or surrounding test area, and also it is fast construction is happening. Full supported hole by casing during the construction, so no need to the collapse of the surrounding material, and limited extrusion of the surrounding soil due to these are the advantages. But there are some disadvantages. We can say based on the relative this disadvantage based on the relativeness. It is based on the other techniques. This disadvantage that is the friction angle of sand is lower than the stone column. So due to that stone is take greater load, that means greater shear strength. That means they take greater load than the sand. So these one of the disadvantage of the sand compaction column. Uh, Second is casing penetration and extraction induce the smearing surrounding the soil. That means due to the penetration and extraction of the material, the surrounding smearing zone is created. This is disturbed zone is created. Due to this disturbed zone, the drainage path is reduced. After that, when the vibration is created, the liquefaction is created. The soil is not, the water is not easily dissipated due to this smear zone, and like that, the strength of the soil is reduces due to the liquefaction. Again, insufficient permeability as vertical drain during the earthquake. That means when the earthquake is happening, the liquefaction is happen. Uh, Due to this liquefaction, excess pore water is created. This pore water pressure may not dissipated due to this insufficient permeability. That may causes huge strength reduced that causes huge reduction in the surrounding soil. So these are the disadvantages of the sand compaction column. Moving to the next slide, it is discuss about the stone column. Stone column is advantage is that stone is very fast and easy and have higher strength and stiffness than the sand compaction column. This again it is related to the sand compaction relativeness shown here by the sand compaction column. So an installation of stone column by bottom feeding method do not create generate spoil. Spoil in the sense do not create debris due to the by bottom feeding method. So these are the advantages. There are some disadvantages also. Top feeding method generated spoil which is not environmental friendly. If we apply this created the stone column by top feeding method, flying debris is created. Due to this flying debris, surrounding environment is hazard is created in surrounding environment and which is not environment good for health purpose in humans, uh, and also have lower strength value than concrete column. Obviously, because concrete we control the design of the concrete, achieve we maintain the cement or sand and aggregate. By maintaining the cement and aggregate, we achieve our goal. So by that way, this have lower strength value than the concrete column. Moving to the next slide, coming to the control modulus column. These advantages are these have strength and modulus according to the project needs. That means what are if you need what type of targeted value, by that way we only go to that. Okay, this technique. That means we control the strength and modular for our project needs and higher strength and moduli than the granular collaboration. That means for stone, these control modulars have higher strength than the stone collaboration. And installation is fast in real-time monitoring and without any vibration and spoil and no issue of whole collapse. That means this hole is created by reverse flight alert. So this technique is suitable to not collapse the hole. And also low mobilization cost. Because after compression one point to go to another point, mobilization cost is very low. So some disadvantage is that this technique is very expensive, very expensive, not readily available. Use if big project like Met Foundation or like that very big project, only that technique is used. And installation may difficult in soil with rock and boulders because we have to cut the soil and make the hole by reverse order. If there is present any rock or boulder, they may be cause very difficult to installation this reverse flight orders. So these are the disadvantages. Now coming to the function, how it is there are how this column is function during this compaction. So there are a few functions: so densification, load bearing, reinforcement, stress distribution, and drainage in geotechnical application. Densification, in the sense, we densify or compacted our ground by inserting this composite column. Load bearing, in the sense, the surrounding soil is loose or very weak in nature, and this composite column is very strong in nature. So the maximum load is transferred to the bottom of the very section, bottom of the column by this composite column. Maximum load is transferred by this column only. And reinforcement, like that, when we apply this composite column in different location, or reinforcement type soil reinforcement type nature is created, which is good for our surrounding soil. Then stress distribution. It is also serve as stress distribution. That means more stress is taken by the composite geomaterial and less stress is created taken by the surrounding soil. So more load can be transferred to the ground through the composite and ground is stabilized. Sometimes it is also served as the drainage, like the stone column or sand column. That means it is permeable. So if you apply the uh, permeable in nature, if during this liquefaction, this may serve as a drainage path and easily dissipate the excess pore water pressure. So it can also serve as a drainage. And one conclusion is drawn that the function of densification is mostly done during the installation of the column and not significantly when the soil is saturated and cohesive. That means the densification function only done when the installation purpose. After this densification is not important for us, and because when the soil is situated and cohesive. Other function may same as further during the service period. Now here some points are given for different researcher based on their research that granular columns can serve as a drainage path to soft soil. Concrete column can also accelerate the dissipation of excess pore water pressure in soft soil. The acceleration of consolidation of stone column reinforced composite foundation is attributed to the drainage of the column and reduction of the vertical stress on the soft soil. The acceleration of the consolidation of the composite foundation by low permeable columns is mainly attributed to reduction of the vertical stress on the soft soil. So these are the few conclusion is given by different researchers based on their research. After that, they are given and concluded based on the deep replacement method. So this is also important based on your exam purpose only. So now we can start the loss transfer mechanism in deep replacement method. So in load transfer mechanism, we now discuss one by one different types of load transfer mechanism in deep replacement method for composite column. In geotechnical engineering, two type of load transfer mechanism is used. First one is equal stress, the second one is equal strain. Equal stress is applied for flexible footing, a flexible type of nature, and equal strain is applied for rigid footing or rigid type of nature. So two ideal condition is used in geotechnical analysis. The example of rigid loading is rigid footing, and flexible footing loading is tire pressure, or we can say flexible footing like pavement or bituminous pavement. So it is said that if there is equal strain in the surrounding soil, the composite column, which is made of good material and also plus with some surrounding soil, like that, one composite column. One is good material, that is stone, like that, and some surrounding soil which is depressed or compacted. Based on these two, one composite column is created. If we apply equal strain, or we maintain the equal strain for this composite material, or we can say column reinforced soft foundation, then the column carry higher stress than the surrounding soil for equal strain, because the modulus of elasticity. That means the column has higher modulus of elasticity than the surrounding soil, so it can take higher stress than the surrounding soil. So if we say that one definition is created by that, one term is new term is created by that is stress concentration ratio. In stress concentration ratio is that the ratio between the stress of the column to that the surrounding soil is defined as the stress concentration ratio, and it is often used for describe the loss transfer mechanism only. Okay, so first is we describe the equal strain method. In equal strain method, when we apply the equal strain method, the maximum load is carried by the column and the lesser load is taken by the surrounding soil, because the column has higher modulus of elasticity than the surrounding soil, and one term is given here by the stress concentration ratio. If we say that in equal strain method, the stress concentration ratio always greater than 1, because the stress on column is higher than the surrounding soil. Now we come to the equal stress method. In equal stress method, when we apply the equal stress method, column have settled less settled than the surrounding soil, because column has higher modulus of elasticity, so it can resist higher stress, but the surrounding soil has lesser modulus of elasticity, so it can easily settle down. So we can say that in equal stress method, the stress concentration ratio is equal to 1. In that case, the surrounding soil is more settled than the concrete column. But this will not happen in the case of embankment when you use this column at embankment. Because in embankment, not only has the stress concentration ratio greater than 1, that means stress is higher of column is higher than the surrounding soil, but also a differential settlement. That means settlement of the surrounding soil is higher than the settlement of the composite column. So this more not this load transfer mechanism may not apply for the embankment when we apply this. So now to the next session, we discuss about the load in detail the load transfer mechanism. For that, we discuss the one unit cell. So what is unit cell? We already discussed the stress concentration ratio. Now we discuss the unit cell. Unit cell nothing but the composite column. So if we apply the one good geometrical in between and some compacted soil in surrounding, one composite column is created. Okay. If we need to find out the influence of this composite column, this influence the area up to that what area up to that is one this composite column is called as unit cell. So here it is said that unit cell which consists of one column, we already said the one good material column and a surrounding soil, it is often to analyze the column reinforcement soft foundation. That means one unit cell like here, okay, sorry, if we draw here one unit cell, one column, reinforced column and surrounding compacted soil, one unit cell is created. So one-dimensional unit cell which has not allowed the lateral deformation of the column. So one assumption is created that if we analyze this, our analysis is 1D, so we assume that there is no lateral deformation in the surrounding soil. So, but some scientists, researchers found out that this same thing not happen in real field. There is some lateral deformation and which is also affect our result. That means our settlement and consolidation rate also. But in our analysis, we assume that one day analysis also assume that there is no lateral deformation in our settlement. Based on that, we calculate the stress ratio or stress concentration ratio in the surrounding soil. So moving to the next slide, we find out the uh, or analysis the unit cell for 1D for 1D one dimensional analysis for unit cell, and we applied the equal vertical strain. That means equal vertical strains mean the settlement is equal for the both column and also the surrounding soil. For that, we find out that one formula that means strain is sigma C by dc equal to the sigma s by ds. Where sigma c the stress in column and d is the constant modulus of the column. Like this, sigma s is stress in surrounding soil and ds is the constant in the surrounding constant modular of the surrounding soil. So based on this formula or rearrangement this formula, we can easily find out the stress concentration ratio based on the constant modulus. So we can rearrange it and find out that the stress concentration ratio for 1D is equal to the stress on column divided by the stress on the soil. This is also equal to the uh, uh, constant modulus of concrete column divided by the constant modulus of the surrounding soil. So based on also we can find out the constant stress concentration ratio for 1D unit cell. In the next slide, there is one chart is given for different types of analysis. Our analysis is 1D elastic, so we follow only this chart. But some researcher is also analysis or consider the lateral deformation. For that there is some reduction is happening, and this is called 3D elastic column. Further, some researcher take in consider the non-linearity of the soil, and again this chart is reduced, and also consider the lateral deformation, and again this chart is used, and it is given by 3D elastoplastic column. So now we find out the total stress or total load applied to the one unit cell for rigid loading. Rigid loading in the cell means settlement is uniform. That means equal settlement. We know that for equal settlement, stress more stress is taken by the column and less stress is taken by the surrounding soil. So if we rearrangement total, if we say that total stress is taken by the one unit cell is sigma z, and total cross section area is A is equal to A, then we can find the force. Total force is the stress into area, which is equal to the total stress is taken by the surrounding soil into the total area is of the surrounding soil, which is find out by subtracting the total area by subtracting the total area of the column from the total area of the one unit cell, plus total stress of the column into the total cross section area of the column. So by this we can find out the total load or total force applied on a one unit cell or one composite material for rigid loading. We remember rigid loading in the sense in the equal strain method. Now we discuss the different failure method. It is the last slide of our session. So there is discussed that four type of failure in composite material. First one, first two are when applied or happen when this column is resting on some hard stratum. Last one is happening when there is no hard stratum is available. So first failure is happen when crushing of the aggregate. If the material is composite material is very weak, the suddenly the column is crushed after applying the load. So, so this is happening, and easily the load is inserted into the ground, that not transferred to the ground, because the material is cast, there is no transformation, and the ground is subsidized. Second one is like when is resting on the hard stratum, the soil is the failure is like shallow foundation failure. তার জায়গায় shallow foundation failure, bearing capacity failure, like that happening. That is also called the bearing capacity failure. Third one is when there is no hard stratum is present. This failure is happen when like pile foundation, that is skin fraction and also the end bearing friction. This type of failure is occur like that through friction or through end bearing also. And last one also, when there is no hard startup, this happening when there is this is called bulging failure. This is happening when the column is too large or too lengthwise is too large. There is some bulging happening after applying the load. This bulging is confined up to a depth of 2 to 3 times of the diameter of the column. So these four types of failure is happening. So here it is said that column are mostly used to carry the vertical load, but sometimes it is used to increase the shear resistance of the software. Under the certain circumstances, columns are subjected to the horizontal load or movement, and the failure modes of the columns under this different loading and condition are different. Columns under vertical compressive load transmitted to the load through the surrounding soil by the side friction and the lateral confinement only. And that's why there is different types of failure is happening. So now I stop my session here. It is already exceeded. Time is exceeded. It is already 8:11, and here we discuss that the vibro compaction and also discuss that deep dynamic compaction. And like that, we completed our session. Now, that there is no time to discuss about the previous year assignment problem. I will share you this on Google Drive, and we can access through it. Also, video is recording. I will share it in YouTube, and by Nptel team we can access this also. And also I congratulate to everyone that we successfully landed our uh, Chandrayaan 3 in moon, and very critical zone also, which is South Pole. Very difficult, and India is the first country in the world to land the any Vikram rover. In the name is Vikram, rover name is Vikram, rover in the moon at South Pole. No country even at this time do that. So we congratulate everyone for that. We celebrate for that, and also I wish for very good for weekend. And now I try to stop our session, and we will meet our session in the next session. We will meet again and discuss about the uh, week six ground improvement technique, which is based on the deordering of the ground improvement and like that. Now we close our session. So thank you everyone. Best of luck for your upcoming days. Thank you.